I'm going to show you how to invent depth first search algorithm and breadth first search algorithm from scratch. So it's better than just learning the algorithm by heart. We're gonna actually solve a real problem, and with intuitive steps we're gonna finally arrive at the depth first search and breadth first search algorithms. We're gonna use Python 3. We're gonna use HackerRank, which is a service that provides problems and also provides code editor and provides capabilities to test solutions. The problem is called red knight's shortest path. This is basically a problem in which you have a chessboard and you have a knight piece, and you're supposed to find the shortest path from one position to another position using this piece called knight. Only in this particular challenge they changed the moves slightly, so instead of 8 moves there are 6 moves. You can see them on the picture, so you can move upper left, upper right, lower left, lower right, left and right. You have to keep an order of priority when you're exploring the possible moves. And it's also important to see how do you index the data structure, the two-dimensional array or list, which will hold the particular knight's positions. So the more low you get, the higher the index of your position is, and the more right you get, the higher the index of the column. So they were kind enough to give us some IO so we can run it and see it fail. They gave us some sample cases in which we're given the size of the chessboard, so it's 7 by 7, the starting position, so 6 and 6 would mean the last position since indexing is from 0, and the last position 0, 1 would be row 0, column number 1, so here. Yeah, and the shortest path would be upper left, upper left, upper left, then left. In the second example, there's no way to actually reach the position with this piece. And there's one more example here, and if we run submit code, we'll actually run 20 test cases. And also we can see on this IO that rows are symbolized by I and columns are symbolized by J, but actually I prefer to use R and C because it's more intuitive to me. So let's jump to the first step. Okay, given that we're supposed to search for shortest path, we'll definitely need to simulate moving our piece through the chessboard. That's why the most intuitive thing is to create a function which returns all the possible moves. So instead of keeping in mind that, you know, lower left is 2 rows down, 1 column left, you just have this function which returns 6 possible moves, and you don't care about particular moves. This is then just a regular search problem, and basically once you have this function you can forget that there's a chessboard or knight to some extent. And we've also changed I and J to R and C for convenience, or maybe for my convenience. And the function possible moves is run before print shortest path, and we can see that it actually returns a list containing of tuples, and each tuple is a position that the knight will take after doing a particular move. So given the starting position, we give to this function r start, c start. We compute all 6 go to positions and add them to a list, and then return this list so that when we print it, we see a list of tuples with the final positions. Okay, next part. Actually, there is a chessboard and it's not infinite. It's n by n. So we should add to our possible moves one more parameter, the size of the playground and the size of the chessboard. And then we should only return the moves which are possible. So, for example, we should only move up if the final position won't be below 0. So we cannot go to row -1 or row -2. So that's why the if statement here. And the same for going out of rows. You cannot have row number -1, and you cannot have row number n because we're indexing from 0, so the highest possible index is n-1. So that's why we have all these ifs. And we've also added one more element to the tuple, just for convenience, the name of the move. So when we actually run the function, we can see what possible moves. When we print this list, we can see what are the possible moves. And yeah. Okay. Usually with these problems, trying to find a general solution is hard, and it's really nice approach to simplify the problem, to solve much easier problem first. So let's imagine that we can only do one move, that we can go one level deep, that our piece can only do the 6 possible, can move in 6 possible directions, but it can only do this once. It can only do one jump, and if it finds if the position it reaches is the go-to position, then it says, what move was done, and that it's required only one move. And if it doesn't reach the position in one move, then it prints that's impossible. And for very simple cases in which the go-to position is actually with the distance of one jump, one move from the starting position, this will work. This will give the correct answer. So I've simulated such a test. I've passed 10 by 10. I've passed 10 so that we have 10 by 10 chessboard. I've passed the first position 5 by 5, and the go-to position 7 and 6, which is 2 to the low and 1 to the right. And we can actually see that our program writes the lists of possible moves, and then it returns that it requires one move, and this is the name of the move, to reach the go-to position. Okay, how did we get this? Okay, first we got the list of possible moves, then we've just printed it for our convenience, and then there's a loop which tries to do each of jumps. You may want to ask why I'm not using for loop. For loop would be more intuitive. Well, when I'm doing search, when I'm working with search related problems, I prefer to use while loop, because the structure I'm iterating through can change during the iteration, during the loop execution. And with function, with for loop, this is also possible, but while loop separates the condition on which we decide whether or not we want to continue loop, and actually incrementing the index, moving to next element into two different separate operations, and it's just much more visible to me. So when we have when the list of moves to do is not empty, we pop from the list. So in other words, we take the last element of the list and save it to move, and this element is removed from the list. And then if this particular move points to the go-to position we are looking for, we're printing the information that, yeah, this is the move, and we end this function because we've found our goal. Otherwise, if the whole loop executes and we're not at our go-to position, we print that it's impossible. Next step. This way, we're only moving by one jump. But let's now solve a harder problem. Let's find any possible path to a go-to position with this knight moves. And let's don't really care about finding optimal path. We can find a path which is really, really long. We can go all over the chessboard. We're just supposed to find any path. And to do that, we basically need line 23 and 22. So whenever we make a jump, we make a move, we see what are the possible moves from the new position, from the position we have just moved to, and then we add these possible moves to our moves to-do list. And by the way, I'm using extend, not append, because append would give me two-dimensional list of tuples, and I just want to have one list of tuples. So this function will execute. This would actually execute forever, because for each move it would see all the possible moves, including the one that has just been done. So we would go again and again to the same positions. We would get memory error when submitting such a code. So we also need to be sure that we're not revisiting the positions we have already seen. That's why we should make an array, a two-dimensional list, a list of lists that includes, well, false, because initially none of the chessboard position has been visited. And by the way, if you want to have such a list, don't use the most obvious way to initialize, because then when you change one element of the list, you would actually change the whole column due to Python quirks and the way objects are treated. So let's first create a whole row, so n elements with value false, and then use list comprehension to do this n times. So we have n by n array of false values. And let's also mark the first node that we're starting in as true, because, well, if this is our starting position, we have visited it, we have no intention to visit it. When we are doing a move, let's only do the move if the position we would reach hasn't been yet visited. Otherwise, we would append possible moves infinitely. And when we visit position, let's mark it as visited. So these are all our changes. So line 23 is most interesting. We've added all possible moves at each step. And when we run it, we can see that we're actually finding the go-to position. In the second case, after exploring the whole chessboard, our program figured that it's impossible to move to the final position with this modified knight move. But for other cases, we can see that, well, we're making a lot of jumps, and then when we're finding the last destination, we're printing the move that took us the last move. So definitely we're finding some solution. The problem is that we can see all the nodes we are visiting, but this really doesn't show us the path we've made. This just shows us exploration of the whole chessboard, and we don't know which particular path, which combination of these moves took us to the goal position. And we also don't know how many moves were needed. And the challenge authors want us to output how long is the shortest path, or in our case, any path, because we are just looking for any path now. And we're supposed to print all the moves that were part of this. And let's store the path so far, and let this information, what path was done until the particular move that we're currently taking care of, and let's just pass it as argument. And let's also do the same with depth. So whenever we're actually making a move, which involves checking all possible next moves, we're deciding that we're going deeper one level. So all the next moves are gonna be moves number 2, right? Because we first execute this with move number. Okay, actually, we check all possible moves number 1. So starting from 0, we add 1, and we're doing all moves number 1. And then each time we're executing this function, we're doing moves number 2, 3, 4, etc. And we're also keeping a string which tells us path that was made so far. And yes, and of course we need to change it both in function definition and in function call. So let's run it. Okay, we can actually see that for first case we've done 11 moves to reach the final position, and from expected output we can see that the shortest possible paths would be 4 moves long, but at least we got some path and we know how deep it was. And same in test case 2, and in 1 it's impossible. So we probably made a lot of moves around we've made a lot of moves around the chessboard, but we couldn't reach the final position after exploring all possible moves. And the question is how to find the shortest path. So look, only now at the very end I'm starting to think how to get the shortest path, because with this sort of problems it's obvious that you're gonna have to do some exploration. That's why the possible moves function, that you're gonna need to code so that you know how deep you are during exploration, what the path was so far, and you need to find a path. And now, only now at the very end, is a really good moment to think about how to make this optimal, how to find the shortest path. Well, the answer is in line 15. Currently, the thing we're doing is called depth first search. So we do move number 1, we move left, we add all possible moves from this position to our list of possible moves, and then we're doing a move from the very end of this list. So we're going one level deeper, one level deeper, right? So we're doing pop, which means we're taking the elements from the right. And with each move, we're exploring the new moves that were added from previous moves. So we will jump that way until we reach the end position, or until we reach a position from which everything else was visited or is out of the board. And only once we've exhausted almost whole chessboard, because we went very deep and no more moves are possible from move number 11 or move number 13, because we would either jump to visit it or out of the board. Only then we're exploring the rest, because we're consuming this list from right. Instead, we can use pop 0, which will actually remove the first element from the list and return it. And well, okay, we passed the test cases. Let's submit the code. We've passed all 12 test cases. Let's go back to depth first search and see what happens. Okay, first of all, we were able to some of the test cases are hidden, but we were able to find impossible paths. We probably got some timeouts because we were looking for really long paths. And just by putting 0 in here, so in other words, just by starting to consume the list from left, not from right, so from first position, not from last position, so from the shallowest possible moves, not the deepest possible moves, we move to the algorithm called breadth first search. And we're doing all possible moves number 1, and only then we're moving to moves number 2. When we do all moves with the depth level of 2, then we're going to depth level number 3. And we're not even using the depth variable to understand that. It's just the order of extending the list and consuming the elements from list. So in this case, if first element is first element out, which is in QE, or in this case in Python list, which we use pop with, then it's breadth first search. If it's first in last out, then it's depth first search. And breadth first search will give us the shortest path, because we won't get to longer path before we explore all the shortest paths. And well, that's it. Good luck. You can find the link to this challenge in the video description. There is a lot of very similar challenges in HackerRank. Some of them won't even require you to print depth and path so far. It's enough to just, say whether a position is reachable. Then you can use both breadth or depth first search, although breadth first search will be faster and shorter. Some may require you to print a number of moves from starting position to final position for each possible starting position.
Some may require some heuristics, like fiddling with the order of exploration. So we first explore towards the goal position, but in general, feel free to explore these problems, feel free to grind some points with your newly learned skills, and good luck.